45 minutes for the whole thing, for both lectures. All right, so I did radiology for one of my first ones. We talked about X-ray generation. A lot of it's physics-based, and a lot of it's a pretty nice story if you kind of know the beginning of it. So what we're going to do today is basically just tell the story from the beginning, kind of to get the understanding of what X-rays are, and then just go from there into how we can use them to our advantage to basically do what we do with them. Okay. So it is nice to have it kind of like in a story format, because that way you don't have to like actually memorize anything. So we'll talk about X-ray generation, then we'll talk about basically how do we protect the patient when we use X-rays on them, and then lastly we'll talk about how to get the best image out of using X-rays and what is a good quality image. So X-ray generation. What is radiation? Well, radiation in scientific definition would be energy propagation through space and time. Now that's just a scientific term, but if you put it in like a layman's term, it just means something that carries energy, something that's propagating, something that's moving through kind of, you can picture it as a wave, you can picture it as a particle, whatever you want to picture it as, kind of like spiraling through this empty area and kind of hitting us with all this energy. It's kind of invisible most of the time. So it's a really weird concept to get if you haven't like done it in undergrad a lot. But radiation is one of those things that happens all around us. We're impacted by all the time. There's solar radiation, there's X-ray radiation, and the cool thing is all of these different forms of radiation, they're part of this spectrum that we call the electromagnetic spectrum. Specifically, electromagnetic spectrum is just one type of energy radiation. Is there somebody? No, okay. So it's just one type. So basically what happens is there's an electric field that's moving in one kind of oscillating up and down, and then there's a magnetic field that's moving completely perpendicular to that same plane. And that's why it's called electromagnetic radiation or electromagnetic radiation. There's other ways that energy can propagate. Like, what is one other way that we know that energy propagates? Like when you feel an earthquake. So an earthquake is basically a movement of tectonic plates. Like tectonic plates slide on one another. They sometimes like fall really quickly, and that will cause a propagation of energy through space and time. In this case, the particles collide with other particles, and as they move out of the wave gets carried away. So this is another type of movement of energy, but it's not electromagnetic radiation because it's not electric and magnetic. So there's different forms of propagation of energy. The ones we are caring about in this case is just electromagnetic radiation. So what's cool about electromagnetic radiation is that there's kind of two ways to describe it. One, you can look at the wave. So you can just be like, well, it's a waveform. It travels in a straight line. It oscillates. So it has a wavelength. It has a certain frequency. And so therefore, I can give it characteristic according to that. You can also look at as electromagnetic radiation as being packets of energy. So you can kind of coagulate all these waves together into a smaller packet, and sometimes these packets, when we talk about them, we refer to them as photons. So when light technically hits our eyes, it comes in packets of energy, and these packets of energies are known as photons. And that's going to become important because a lot of time energy isn't continuous in a lot of ways. Like in, for example, atoms, when their electrons go from one shell to another shell, there's a certain amount of energy that is required between the two shells. It's not continuous. It's not like electrons go up slightly. They go up a discrete amount. And that's fundamentally what's really important. So if you can think of radiation, am I losing anybody yet? Are you good? So radiation, so the basis of it is electromagnetic radiation. So what we're talking about, it has different frequencies, it has wavelengths, and it comes sometimes in packets, which are called photons. That's basically essentially what you should understand at the basic level. So we talked about how else does energy move through space and time. We talked about earthquakes. And then if you look at the frequency of electromagnetic radiation, there's different frequencies a wave can have. And these frequencies will directly fall in this giant spectrum. So electromagnetic radiation can have a really high frequency, or it can have a really low frequency. Now, what's inversely proportional to frequency? Do we know? Wavelengths, because the equation is simply put C equals frequency divided by lambda. So C being a constant, which is the speed of light. So in a vacuum, we know every single time how fast that wave is going to propagate. It's going to be at the speed of light. So if we know that's a constant, and we know the frequency of it, we can calculate the wavelength because it's inversely proportional. So you can look at frequency or you can look at the wavelength, but that's one way to place a spectrum. So you can look at the wave and be like, a longer wavelength will be down at this end, and a shorter wavelength will be down at this end. This will be a lower or higher frequency. This is a long wavelength, so that must mean this is a low frequency. This, on the other hand, is a high frequency, but it's a shorter wavelength. Makes sense. So these things, because they fall on the spectrum, we can kind of arbitrarily divide them into different parts. That's what we did as humans. We kind of said, well, these rays, or this frequency, below this frequency, below this frequency or longer than this wavelength, we're going to call these radio waves. Above this to this point, we're going to call them microwaves, infrared, ultraviolet, X-rays, and gamma rays. The really small part right here is the visible light that we see, and that's what gives us all the color of the rainbow. So what's kind of cool is that even though there's electromagnetic radiation, you can, according to the spectrum, the wavelength that is hitting you will define what it's exactly doing. If it's in the radio wavelength, it might not be very damaging to you because it's a very long wavelength and very low frequency. So another equation that he didn't really introduce, but we talked about in undergrad a lot, is the energy equation. So energy is directly proportional to the frequency times another constant, which is Planck's constant. So it tells us that if there's a high frequency, that wave is usually carrying a lot more energy. Well, not usually, it's always carrying more energy. So higher frequency means higher energy. So that means that things that are down here will be more damaging to us than down here. And that's why we say these up here are ionizing energies or ionizing rays versus these down here are non-ionizing. Ionizing just tells us that when these things, when electromagnetic radiation at this end of the spectrum hits us, it can cause our atoms to lose electrons and create basically radicals at that point. And these radicals are very damaging to us because they can destroy DNA, cause our apoptotic pathways to trigger, and then we go into a whole different lecture. Okay? So that's cool. So radiation, the similarities between all types of radiation is that they all travel at the speed of light in a vacuum. They're all massless. And then they have these equations that describe how they function. So frequency is one way to describe them. Wavelength is another way to describe them. Remember, they're inversely proportional to wavelength and frequency are kind of related to each other. And then energy is basically dependent on the frequency. And the frequency, when it's higher, there's higher energy in that radiation. Okay, everything's clear so far. We're good. This all makes sense. This is the basis of radiation. So then let's talk about making radiation happen. We do it in different ways all the time. So how do we make radiation happen? Well, we can use atoms, and we know when electrons circle around the nucleus, they have a certain, they're in certain shells, right? That's why we draw them like this. This is the Bohr-Rutherford diagram of like an atom. We draw them in little shells. We don't draw them everywhere. We draw them in like the first shell, the second shell, the third shell, and whatnot. And we also know that when electrons move from one shell to another shell, so if they move down a shell, so for example, if they go from the shell 2 to shell 1, they actually release energy. On the other hand, if they move from shell 1 to shell 2, they must have absorbed energy. Does that make sense? Okay? So we can use this kind of idea to actually make radiation happen. So if we were able to kind of force this electron or kick an electron out from this shell, from the inner shell, then this automatically electron will fall down into this shell to complete that one because it's more favorable, and in that process it would give off radiation. So all we have to do really is kind of kick out electrons from inner shells to get this one to come down. Make sense? Basically what we're doing is playing around with atoms, kind of disrupting their shells and making sure that electrons fall down the shells, and as they fall down they'll release packet of energies, and that packet of energy is directly dependent on the frequency or the kind of what shell transition it is. Nobody cares. All we care about is that the electrons are moving out from the inside and then the outer electrons are falling in, which is releasing energy. Okay? So that's the scientific way of looking at it. Let's talk about like what we care about as dentists. Okay? So how do we make radiation happen? Well, sun does it all the time. We know solar radiation exists. How does the sun do it? Well, it has nuclear fission. It uses all these particles. It's very chaotic. It's not very controllable. Unfortunately, we can't put the power of the sun in an extra machine. So what we use sometimes, which is more reliable, is called electricity. All electricity is just movement of electrons, right? And we do it all the time with light bulbs. So light bulbs are usually working at, 110 volts? And it's just current moving through this tungsten filament. Okay, so let's talk about light bulbs. Tungsten is a really cool element. It's really easy, to pass electricity through tungsten, but the thing is, it creates a lot of heat. When you pass things through tungsten, you'll realize that slowly over time, if you notice tungsten, it becomes red hot, and then becomes blue, and then becomes almost white, which is the light we see. What is happening? Well, what we're doing is passing electrons through this tungsten filament, we're creating heat, a lot of heat, we're wasting a lot of resources, but also at the same time we're causing electrons in the tungsten to move in different shells. So we're kicking electrons out, electrons are falling down, they're releasing energy, and if they release energy at the right frequency, remember in that small spectrum of visible light, then we see color, we see a light. Okay? So that's kind of cool, but what we want to do is we want to make X-rays. Remember, all we have to do is make sure that when that energy is released here, that frequency falls in the spectrum really far down here. So to get that to happen, we have to put in a lot more energy. So when light bulbs work at 110 volts and they make a visible light for us, why not use 70,000 volts in X-rays to make our X-ray radiation? So in X-rays, we use the same concept as light bulbs. We use tungsten filaments again. We use 2 tungsten filaments. We'll talk about the circuitry. We need to use much larger voltages because we need to make much larger energy changes. And that's basically the same concept there. So we're making radiation using electricity again. And remember, because we're using a lot more voltage, we're making a lot more heat. So light bulbs and X-rays are not very different. We're making radiation in both of those things. Both of them are electromagnetic radiation. The only difference is where they fall in the spectrum. One of them puts them really high up on the spectrum. One of them puts them in the visible light spectrum area. Okay, so far so good? Are you good, Jack? Yeah. All right, perfect. So let's talk about Crookes. So I didn't go into much detail about all the guys. He does that in his lecture, so you can just look them over. But the important concepts were Crookes tube, which he talked about a very little bit. Basically what it had was, it had this partially kind of vacuum chamber. It was made out of glass, and there was some air inside of it, but it was kind of, it was made to be very little air inside of it. And there was a cathode end and there was an anode end. The cathode end was your negative side. That's where the electrons came in. And then the anode end was the positive side. Okay, so cathode is the negative side, the anode is the positive side. So far so good? So when the current came in through the cathode, it heated up the air, it caused ionization at that level, and it shot electrons out. And that, when they were shot out, they went through the anode and the circuit was complete. So everything is good right there. Everything is good? Okay, so cathode is the one that's shooting out electrons. Remember, always cathode. Look at cathode ray gun in TVs, like really old TVs. Cathodes shoot electrons. So that's basically what it does. And the anode is where basically they go back and they complete the circuit. Okay, so that's not the interesting part. The interesting part was that because the anode was located in that little kind of hinge part, some of the electrons missed and they shot at an object, and behind the object you caught the shadow. So it's kind of cool. And if you put some gases in here, like some neon and stuff, you would get different colors, which was really cool. The cooler part was they noticed that this kind of like process was also making other types of radiation, specifically X-ray radiation. So they use a similar concept now in X-ray machines to make X-ray radiation. So what happens in X-ray radiation? They're a little smart about it. Here, they didn't have an electron cloud. They were just making electrons happen when current came in, which is a little more energy requiring. So you put voltage in through the, you run electrons from one side, you get inside the cathode, you heat up the air, you cause electrons to form and then shoot across. Instead, in X-rays, what they do is they actually create an electron cloud. Okay, so how do they do that? So in the cathode, there's a tungsten filament. Okay. And then in the anode, there's another tungsten target. So the cathode and the anode are still the exact same as the Crookes tube. Nothing has changed between that. Instead, in the cathode, you also have a tungsten filament, and in the anode, you have a tungsten target. So the tungsten filament is where you're going to make your electron cloud. And the tungsten target is where you're going to shoot the electrons at. Okay? So the first part right here, to make the electron cloud, you have to give some energy to the tungsten. So all you do is basically run a really small voltage circuit. So you basically, this is called a low tension circuit. So you run a little bit of voltage through the tungsten filament. This heats up the tungsten. We know that happens in light bulbs all the time. This, as it heats up, electrons come off the tungsten because heat causes them to kind of fly away from the atom, if you can picture it, and they hover in that kind of region. They're ready to go. Okay? So electrons are standing here, kind of picture them as a cloud above the tungsten filament. So far, so good? This is the cathode, this is the anode, there's a tungsten filament here, a tungsten target here. A little bit of current is ran through here. This is called a low tension circuit. This is what happens when you turn on the on switch in the morning, that's what he was talking about, and you create a little bit of an electron cloud. Okay? Hey man, how's it going? And then after that, when you're ready, you actually turn on the 70,000 volt circuit. So when you turn on the 70,000 volt circuit, the cathode, just like before, becomes really negative. And remember, electrons were floating right above the tungsten filament. So when you make this cathode really negative, what happens to the electrons? Do they get repulsed or do they get attracted? They get attracted towards the anode, or they get repulsed away from the cathode. So they basically get shot at the second piece of tungsten that was already here. Okay, so let's go over it again. So cathode, tungsten filament, low tension circuit. So you heat it up very slightly. You heat it up and it creates an electron cloud. Nothing else has happened yet. When you're ready to expose, you press the exposure button, and that shoots 70,000 kilovolts, or 70 kilovolts or 70,000 volts of electricity through this high tension circuit that goes between the cathode and the anode. This makes the cathode really negative, the anode really positive, and the electrons that were already hovering here shoot across from here and hit the tungsten target. Now, what happens to the tungsten target? Well, that's kind of cool too. Oh, that's I'm doing it. So tungsten target. So what happens is you basically have these electrons that are coming in at very high speeds. Now they can do one of three things when they get to the tungsten target. They can either go and hit the nucleus directly, which is a very rare occurrence, and that's why it's called rare occurrence, because nothing happens at that point. Electron hits the nucleus, energy is absorbed, nothing happens. So that's a very rare occurrence because there's a lot of things floating around. The second thing that is more likely to happen, the most likely to happen, is that they kind of go in there, but they get disrupted because they're getting closer and closer to the nucleus, but they get deflected off their path, or they kind of just like slow down a little bit because they're getting closer to positive ends, and as they leave, they emerge in a different path, and that's called the Bremsstrahlung against radiation. I'm saying that right, but Bremsstrahlung. So what that basically means is that as they come in, Bremsstrahlung just means braking acceleration or braking radiation. So it just kind of slows down the electrons that are being shot. And that creates radiation, but depending on, I guess, okay, let's pretend this is the first one that's coming in. So this is the first electron that came in from the cathode. It goes to this first tungsten target, does the Bremsstrahlung path, I guess, so it kind of misses everything, slows down a little bit, goes up that way, releases some energy and radiation, and that radiation has a certain energy coming out, okay? So let's say now A prime goes to a second tungsten target atom, does the same thing again, but now less energy comes out of it, so therefore now you've got another Bremsstrahlung radiation happening, but this time because the energy of the electron coming in is less, the radiation energy leaving is less. So because of this, you've created like a spectrum of radiation coming out of the tungsten target. Okay? So rare occurrence, no radiation comes out. Bremsstrahlung, you get basically kind of like a spectrum of radiation coming out. Okay, some of it is really short wavelength, which is good. Some of it is longer wavelength, which is less useful. Okay, the last one is the characteristic radiation, which is kind of like characteristic of tungsten. So this is basically where the electron goes in, it hits one of the inner shell electrons of the tungsten target, kicks it out, and that causes radiation. And that's characteristic of the target, which in this case is tungsten. So that will give you the characteristic of the tungsten thing. It's just radiation, but it's just a very significant kind of radiation, and you can detect it. That's why it's called characteristic radiation. So one of three things can happen when the electron comes in. Either it can hit the nucleus, nothing happens. Bremsstrahlung in the first target, Bremsstrahlung in the second target, and then it can do whatever after that to the third target, fourth target, whatever. By targets, I mean different atoms in the target. And that gives you a spectrum of radiation. And then lastly, characteristic is when it hits the inner shell electron, kicks it out. Okay, so this will give you a wide range of X radiation coming out of the system, basically, coming out of the target. Another thing that gives you variation is that we use alternating current in some of the machines. So that basically means at the cathode end, when you're shooting from the cathode end, it's not 70,000 volts all the time. Sometimes it's more, or sometimes it's less. sometimes it's 70,000 volts. So basically, because it's alternating up and down, sometimes the electrons that are being shot here have less energy, have more energy, or have 70,000 volts. You know what I mean? Like it's alternating. So when they hit that tungsten target, they're not going to always have the same radiation coming out. So now there's two things causing variation in that radiation, and we have to deal with that because some of that radiation is useful to us, some of it's not. And we don't want to hit the patient with radiation that's not useful to us. Okay? And then we can fix the alternating current by using rectifiers. And that's what they do in some of the machines. Alternatively, we can use a DC current, which is nice too. Okay? All right, so that's the radiation part. That's all there was basically to it. So protecting the patient is important. There's a couple of things that protect the patient. So remember the Bremsstrahlung and the AC that cause the spectrum of radiation? If you want to take out all the stuff that's not important to us and keep only the shortest wavelength, we use aluminum filter. That basically filters the radiation to take anything that's longer than a certain wavelength out of the equation. Because remember, shorter wavelength is what we want. That's the one that's good radiation because it's higher up on the spectrum. It's going to do the most damage, but it's also the most useful for us. So anything that's less than 70,000 volts in energy, if we're using 70,000 volts, the cathode and the anode, we'll use a 1.5 millimeter aluminum filter, he said. And if it's more than 70,000 volts, which are some of the machines here, we use 2.5 millimeters. Next things he talked about was the quality and the quantity of X-rays. So remember we talked about the electron cloud at the beginning that was created by that low tension circuit. So there was a tungsten filament. There was a tungsten filament right here. And remember we created an electron cloud here. So if we want to create a bigger electron cloud here, we will just increase the amount of low tension circuit right here. So that's what created electron cloud. So we can do that by changing to milliamps. So if we increase the milliamps, we make more electrons here initially. So then eventually when we shoot all the electrons at the tungsten target, we'll get more radiation. So that increases the quantity of radiation.
You can think about that because the amp is
per second. Exactly, it's per second, exactly.
Second is more quantity.
Yeah, perfect. So milliamps per second, if you increase that, you have to do less exposure because you have a larger quantity of electrons being shot at the tungsten target. That means more radiation in general. But how do you improve the quality of it? That means that it has a higher penetrance. It means that it can it can go through things much further. It can go through more dense things. That can only be done by increasing how much potential is between the two things. And that was controlled by the 70,000 the volts that we shot. So if we increase from 70,000 volts to 90,000 volts, we'll increase the quality of radiation. So there's two things, quality and quantity. Quantity is by the electron cloud, or also the milliamperage, that's what he said. And then the quality of X-rays is basically increasing that kilovoltage. So if we use more than 70,000 volts, we can increase the quality. So it will penetrate more. Okay, so far so good? All right, ways to protect. So we want to use the longest rectangular collimator we can. And the reason for that is because when X-rays come out of that tungsten target, they're basically diverging. As soon as it's shot out of the tungsten target, they're going to be going in every single direction imaginable, like a flashlight. So we want to use all the rays that are going kind of parallel rather than using the ones that are going spread out. So we use a long collimator so that as it travels along the collimating device, the lead can absorb all the diverging ones, and the most parallel rays come out of the end of the collimator. We also want to use a rectangular one because, again, it's less ionizing radiation to the patient because 60% reduced. The next problem, though, is that if we use a longer collimator, we have to realize that as it gets further away from the patient, the radiation has less of an effect at the end because the inverse square law tells us that the intensity of the radiation reaching the patient is inversely proportional to the square, that's complicated to say, but the distance, as you double the distance, the intensity of radiation at the end decreases by a factor of 4. So if I double the distance, then the patient will get 4 times less radiation at the end of it. So you have to kind of account for that by adjusting the exposure time. So if you get a longer collimator, increase your exposure, like if you double the collimator size, increase your exposure time by 4. Exactly. The next thing was one way to measure it, how good your penetrance is, by using the half value layer. So this is when a person comes in and to test your machine, he'll put like a filter in front of the machine and measure the radiation after putting the filter and before putting the filter. So whatever amount of filter it takes to reduce the radiation by 50%, that's the half value layer. So if it's if you can kind of like, if you kind of put it in your head, so like imagine that aluminum filter, we're talking about the 1.5 millimeter filter. Let's say that was going to be not adequate enough, and you needed to reduce radiation by 1/2 times more. You double the length, double the size of the aluminum filter. So if you make it 2.5 times, then it would kind of reduce the material, or reduce the radiation by 50%. So that's the half value layer. Yeah. So what you want to do is basically adjust the quality and the quantity of X-ray to make it so that it's sufficient to get the results that you want, but not more than you need. That was it. That was the ways to protect the patient. That's all he talked about in the 3 things. Image formation. So he talked about a couple of things that define what's a good image. So the density. So the density he measures as being the darkness of the image. So how dark is the film? Wherever the radiation makes it through the patient and hits the film, it will turn dark. Wherever it doesn't penetrate a target, it will stay white. Okay? So density is directly dependent on what? Oh my God, this is horrible. Yeah, so it's dependent on a couple of things. So if you can imagine in your head, if we used a higher kV, so a higher voltage, so what would that do to density? Would that increase density or decrease density?
It makes more contrast.
It makes more contrast, yes. Now we're giving it. Okay, so if I'm using a higher voltage between the anode and the cathode, are the electrons being shot faster or slower? Faster, because I'm making it really negative on one end and more positive on the other end because I'm using a higher voltage difference, and that means the electrons being shot at the target are way faster. That means that when they get to the target and do all the Bremsstrahlung and the characteristic radiation, it's going to have more energy. And that energy is going to directly come into play when it penetrates deeper into all the tissue and stuff, okay? So that's one of the ways. What about quantity? So what if I have a larger electron cloud? Is that going to increase my density on the film?
Yes.
Yeah, so if I'm shooting more electrons at a patient, there are bound to be more electrons hitting the film at the end of the day. Make sense? So quality and quantity of X-rays will tell you how dark a film is going to come out. If you have really high penetrance, let's say it's a kid, and you put your exposure time as being really high for like an adult patient, everything's going to kind of make it through the patient. And so that means that your film is going to come out really, really dark. Okay? What else can control it? Well, the viewing of the film itself. So if you don't view it in proper light, then you're not going to see all the white. So therefore, it's going to look a little dark. So that's important. The process of how you process the film is going to play a big role in density. And the film itself, like the type of film that you use, can play a huge role in how dark it turns out. So that's a couple of things that define density. Contrast. So, oh shoot, I had them. I forgot to print it. Anyway, the demo. Jesus, that was going to be good. All right, but let's see if I can find it. We'll do it after. Anyway, so high contrast. What is high contrast? He talked about it in class, if you guys remember.
Contrast just means that you can see well between different.
Yeah, so contrast basically like how well defined are the shades of gray between like two areas. So like let's say you have a slightly gray area versus a slightly darker gray area. Can you see the difference between the two? And if you have a high contrast, usually you can't see the difference very easily between the two. But low contrast, you can. So high contrast basically means that above a threshold, everything appears white. So it means that, so let's say you have rays trying to penetrate a tooth, okay? So at a certain point, if you have low penetrance, so you don't put a lot of energy into the rays, they're not traveling that fast, the radiation doesn't have that much energy in it. So it's going to hit a certain point in that tooth where that tooth is going to be too wide. And anything wider than that will all appear white. So at a certain point, everything's going to look white on the film because nothing's going to get through the tooth. Okay? So how do you fix that problem? Well, you increase the penetrance. You increase the amount of voltage between the 2 points. Right? So you increase the quality of X-rays to get more penetrance. So it's kind of the opposite way of thinking. So high contrast will come from having not enough voltage in your rays, or not having enough energy in those rays, not having enough penetrance in those rays. On the other hand, low contrast, which is the ability to see kind of different shades of gray in between those two things, will come from having a high penetrance. So if you have a high quality of X-ray. So you want low contrast. You want to be able to tell all the colors apart. So if you ever put your TV on like a low contrast setting, it's usually better looking for the shades of gray. Sometimes we put in a higher contrast, we just want to see like the dark blacks. But we lose a little bit of the details. So the next thing, did we miss anything? Yeah, that's about it. Density and contrast was a big deal. So you want to get a low contrast and a good amount of density on there, but not too much. The next thing was the image detail, the sharpness of it. Now this is controlled by a couple of things. So the first two things are more theoretically important. The last thing is more like actually important. So umbra is like umbra is like basically the actual image, like how detailed is your image. The penumbra is like the shadow around the image. And so usually you want the most detailed umbra and you want the smallest penumbra. So how do you get the most detail in the umbra? Well, you get the smallest target point. Imagine a flashlight. What's going to have a finer control on the rays? Is it going to be a laser or is it going to be a big flashlight torch? A laser is more pinpoint, right? And so therefore, if you have a smaller target making that light, you're going to have less of a divergence. So you try to get the smallest target possible. And one of the ways to do that is by, first of all, picking the smallest tungsten target. And second of all, is by angling that target in a certain way to kind of decrease the size of it. So you want to make it as small as possible in the machine. And that can be a problem because sometimes when you want to increase voltage, now you're shooting a huge amount of electrons at a really small target and it's going to get really hot. So that's where you have to cool it a lot. And that's why we have oil in the machine usually cooling the target. Okay? The next part is the focal film distance. So we know that the focal film distance will tell us how far away the film is from the actual generation of the X-rays. So the X-rays are made here. The film is here. You want to increase that distance as much as possible. Why do we want to do that? Because when the rays come out at the end of it, they're going to be most parallel. So if we have it like really close, the rays are going to be diverging a lot, and so therefore you're going to get a lot of magnification of the object. It's going to look a lot bigger than it's supposed to be. It's not going to be as clear. It's going to be distorted. And so if you want to keep it as small, like as real size as possible, you want to have that focal film distance be really big. So focal film distance basically from the tungsten target all the way to the film. Okay. The next thing you want to do is reduce the object film distance. So that's as soon as the X-rays hit the tooth, you want them to hit the film right away. Because the further away they travel from the tooth to the film, the more chance they have of scattering. And so you're going to lose the detail in that. So that's going to be the second thing. And lastly, you want to keep the film and the object as parallel as possible to each other. So if you keep them parallel to each other, you get the exact size of the tooth. Rather than if you keep them like in a different angle, then the tooth might appear smaller or bigger than it's supposed to be. And the only reason we wouldn't do parallel film and object is because we can't. So if there's angles that we can't get to, then we would use the bisecting method, which he showed in class. The penumbra is a shadow, which is basically the thing behind it. You want to keep that kind of area small. And that's going to be possible if you do everything in the umbra. If you keep them parallel, you use a long collimator and whatnot. And lastly, the most important thing for good images is no movement. If you have movement, that's more important than anything else. Basically, you can have the best focal film distance, you can have the most object film distance, but if you have movement, it's going to come out blurry. It's not going to look good. Summary. So X-rays are in the ionizing range of the EM spectrum. We use electricity to generate X-ray by bombarding tungsten with targets. So intensity is dependent on all these things we talked about. So quality was the kV. So if we increase kV, we increase the difference between the anode and the cathode. We shoot electrons at a higher energy. We create radiation at a higher energy. That means that you're going to get low contrast because you're going to penetrate more things. So that's kind of all relating it together. Quantity was making more electrons. So you heat up that tungsten filament initially, create a larger electron cloud, you shoot them all at the target, you get more radiation in general. So that's quantity of radiation. Exposure time, basically this is dependent on how far away the film is. Remember, because intensity was inverse square law, so how far away the film is will dictate the exposure time, how much radiation are you producing, so quality, quantity, all that stuff comes into play. And lastly, the area, so if you use a rectangle instead of using a circle, you're actually focusing your rays on a smaller area, so that's good. So a detailed umbra and a minimal penumbra is characteristic of a good image. Movement is the primary reason for a bad image. So now the best way to use this information is to kind of apply it. So let's do some discussion, okay? You take a radiograph, but the periapical area is either completely white or completely black. How do you fix the problem? So what's happening? Perfect. So you have high contrast. So first, that's important. That's good identification. Because you have completely black or completely white, that means that you have high contrast. So what does that mean? Not milliamps. You'd want to increase Voltage, perfect. Yeah, penetrance. Perfect. Because what's happening is that we're shooting radiation.
Would either one increase that?
No, either one would increase density, but not contrast. Contrast depends only on penetrance. So what's happening right now is that you have radiation at a certain energy, but that energy is not enough to get through whatever you're trying to get through. So at a certain point, everything above that threshold is appearing white on the page. And yeah.
So a low contrast also gives you better penetrance?
A low contrast comes from having better penetrance. So like by having higher penetrance, you can get low contrast. So it's just a way of identifying what is playing. Yeah. So by having more energy in that radiation, by having a higher voltage difference, you can create low contrast. Yeah. As let's do that one. So a nervous but smart patient asks you why your position indicating device looks so dangerously long. Explain the reason. So why would you want to be having a long collimator or a long position indicating device?
Because the longer it is, the more you can use just the parallel rays. And
Nice.
the less radiation.
Fantastic. Okay, so exactly. So at a tungsten target, you're making all this radiation, and as soon as it leaves the target, it's diverging. You want to get rid of all the diverging rays. You want to get all the parallel rays coming out, because that way you can get the sharpest image and the least magnified image possible. Okay? What is one of the smart ways that machines can make the focal film distance longer without using a longer collimator? So do you guys remember that image in the class? So what they do is they place the tungsten target at the really back of the machine, so in the back of the head, so that way you have all of the head to collimate as well as the collimator. So instead of having like it right in the front and the collimator being 16 inches long, you place the tungsten target in the back of the machine and the head itself is 8 inches long, then you only have to put an 8-inch collimator in front. So that's kind of one way to do it. And they have a really cool picture if you see it. You'll see it next time. Sure. And then lastly, this one's a more complicated one, so just take your time. So a frantic dog owner comes to your office with his dog wincing in pain from a dental issue. Let's assume that dogs have more dense and thicker teeth than humans. How would you use your knowledge of X-ray imaging to take a good radiograph? So what would you have to do?
You have to increase penetrance.
Okay, fantastic. That's one of the things. So you have to increase penetrance. What else? How would you increase penetrance, by the way? Nice. Okay, but can we do that in our machines?
No.
Good. Okay, so it's interesting because he talks about all the theory behind it. Unfortunately, we had to know the theory for the test, but how would we in reality do it? Because the only thing we can control in a machine nowadays is, what do we control in the machines upstairs? Do we control the kilovoltage or the milliamps? No, that's already preset for us. Exposure time. So what would we do to exposure time?
So you'd
Increase exposure time. Fantastic. What else do we have to do? It's a dog now, so we have to be careful. So what else we have to do? We have to make sure what's the best way to get a good quality image? What's the most movement, exactly, because the dog moving around, you have to make sure he stays still, exactly. So remember, those are things that you can kind of apply. I mean, if you had a dog emergency ever, you'd be good. There you go. So make sure you do that. Yeah, so you'd want low contrast by increasing penetrance, and the only way you would really know how to do that upstairs by using your exposure time. And if they ever ask you in the middle of it why your thing is so dangerously long, you'd be like, well, because of parallel rays, and that's it. So that's discussion. Yeah. Thank you.